wrong. Now, to help you appreciate the orientation of these alcohols and to give you a couple shortcuts on how to memorize this, let's go ahead and go to my ISIS draw. Here is an example of alpha D-ribose. Notice the term. This part right here, D, refers to the orientation of this hydroxyl group in blue. If I were to sit there and make a L-ribose, for example, then it would look like this. The only difference is the mirror image for an L-ribose. Oops. Would look something like this, provided each of the hydroxyl groups were flipped. So this right here would be an example of alpha L-ribose, and we can determine whether it's D or L by the second to bottom alcohol group, second from the bottom alcohol group, which is highlighted in blue. Now, as I said, the body or organisms in general, they prefer only one type of enantiomer. So all the sugars are always going to be in D enantiomer form. If you have L present, again, the body's enzymes wouldn't know what to do with it, and it would just sit around waiting to be collected by the garbage, or it might participate in unwanted reactions, which you never want inside a living cell. So, next thing we need to do is go ahead and I'll talk about alpha in a second, but for right now what we need to do is create the Haworth structure. So, first thing you'll notice, but before we do the Haworth structure, let me point out a couple other things. For the sugar molecules, notice how they always end in a alcohol, which I've highlighted, so in black. And notice how they always begin, not always, but for these starting ones, they'll begin with a carbonyl group. Now, the best way to memorize these is we already know that the alcohol on the bottom is going to be to the right, since it's always D. These over here, you want to go ahead and memorize. I always memorize it like a game code. So just as you had to put in the game code to get the extra bullets or shielding or whatever, I memorize this as right. And that's how I know that on carbon 2, this alcohol is going to be to the right, this carbon is going to be to the right. Now, as far as sketching the Haworth structure, let me go ahead and take you through the transformation. So first thing I'm going to go ahead and do is make a copy, and then I'm going to show it rotated on its side. This alcohol group right here is going to be the one participating in the cyclic hemiacetal reaction. In the Haworth structure, it's partly line angle, so we don't have to worry about showing the hydrogens like we have to do in the Fischer projection. So in this case, I'm just going to get rid of these hydrogens because they're in the way. They're still there, they're just implied. Next thing we're going to go ahead and do is start to create this Haworth structure. So I'm going to go ahead, and this entire thing is going to start wrapping around. So I'll show you it wrapping around like a transformer. This alcohol right here is going to flip around and it's going to form a brand new covalent bond with this carbon. At the same time that it combines with this carbon right here, this oxygen is going to go ahead and combine with this hydrogen. So let me go ahead and draw a bond. And at the same time, this hydrogen had popped off and it formed a brand new bond with the hydrogen. So that oxygen formed a brand new bond with the hydrogen. So now we have OH. Notice carbon 2, carbon 3, we memorize the game code alcohol group, so to speak, as being to the right. And when it comes to converting it from the Fisher projection to Haworth, right is always going to be facing down. Right is always going to be facing down. So if carbon 2, carbon 3 is right, then these should be facing down. So I'll scoot these over to a bit. Now it doesn't have to be perfectly vertically down, as long as it's so if this were like an equator, as long as it's lower than the equator, so to speak. So here's my imaginary equator I'm making right now. Notice how the alcohol groups are facing down compared to the equator. I usually use this line right here, the cyclic carbons, as my point of reference for whether it's going to be facing up or down. So let me show you what an up position looks like. This is an up position, and now I'm going to face it down. So notice both of these are down. This right here is called alpha D-Ribose. Alpha D-Ribose. Now, the minute carbon 1, which is highlighted in red, went from an aldehyde to an alcohol, we have now created in this cyclic structure a new chiral carbon. With this new chiral carbon, the alcohol is either going to be in a down position or it's going to be in a up position. So, nature most of the time prefers it in the down position. So, the key to this is if it's facing down, we call this alpha. If it's facing up, we call this beta. Usually they like to use the Greek alpha symbol. Usually on my tests, however, I like actually writing out the words ALPHA for alpha. For beta, it's up. So now you can see in this cyclic structure right here, this is alpha D-Ribose, because it was originally D in the open chain form. And in the heterocyclic form, what we call the Haworth structure. The Haworth structure. You can see the alpha on the chiral carbon, which is in red, and because it's facing down, it's alpha. So, if I wanted to, I could change this. Although it's not found in nature, I could change this to a beta. And the minute I change it to a beta, then this alcohol would be in the up position and this hydrogen would be in the down. So we're always looking at that alcohol to figure out if it's alpha or beta. In this case, it's now beta. I'm going to go ahead and turn this back into alpha since that's how it's usually found. ALPHA. So now it's facing down. Again, I have an imaginary equator that runs through the structure. So if it's below the equator, then it's facing down. If it's above the equator, then it's facing up. Now, this brand new chiral carbon that's formed during the cyclical hemiacetal reaction. First of all, this carbon right here is a example of a cyclical hemiacetal. But in biochemistry, whenever we refer to this cyclical hemiacetal carbon, we like to give it another name. We like to call this a anomeric carbon. Anomeric carbon. So that is the other name for it. So that's the anomeric carbon. So I'll go ahead and put an arrow to that. Although the arrow doesn't like to be twisted. What happens if I were to do this? Aha! I'm good. Alright. So let's show the arrow going right here. And I'll highlight it in what else? Red. I'll even highlight this one in red. And that's the anomeric carbon. So in this case, to repeat myself 1/millionth time, on the anomeric carbon we have an alcohol which is facing down. So this is in its alpha position on the anomeric carbon. So we call this alpha D-Ribose. I'm only going to ask for alpha D-Ribose for the Haworth structure. And you should be able to draw it just as you see here. Sometimes where it says C2OH up here, I'm not a big fan of this. I actually like having it written like this, where you can actually see it in line form. Now, if you put CH2OH like this, then I'd still give you credit, or you can write it in this form. Either way. We love using the Haworth structure because it makes it easy representing a molecule in its 3D spatial arrangement. As a point of reference, if I were to sit there and show you the Wedge dash structure, it would look like this. Can you see how ugly it is trying to draw the Wedge dash structure? I think it's much easier to appreciate using the Haworth form. Consequently, you'll be tested only on the Haworth cyclic sketch form. Let's go ahead and move on. Going back to our slides, in this case, it says Deoxy Ribose. Notice the only difference between ribose and Deoxy Ribose is that highlighting with my yellow pen, there's a oxygen missing. So here on the left frame, we have ribose. Over here on the right-hand frame for the open chain, we have a missing oxygen. So this is Deoxy Ribose because it's missing the oxygen. If you're to sit there and draw the Haworth structure, notice there is no alcohol group represented. Technically, in the Haworth structure, this part right here is considered line angle. And there's two hydrogens on this portion of the molecule. It's just implied, like any line angle structure. So we tend to draw it either like this, or we draw it with just a hydrogen but no alcohol connected. Most people just simply draw it the way you see it right here. By removing that particular oxygen in this location, Enzymes, which naturally break down ribose for energy, no longer recognize it and cannot break it down. This is important because many structures inside your body contain this particular unit in making its in helping out its structure in its overall form. For example, Deoxy Ribose is used all the time in creating the backbone of your DNA molecule. So everything is Deoxy Ribose. So that way the enzymes don't sit there and munch up your sugar units, destroying the backbone and therefore the genetic material inside your cell. So, I've beat that to death. Let's move on to glucose. Here is glucose. Glucose has 6 carbons. Notice the pattern for these. So notice it begins with a aldehyde and it ends with a alcohol. Also notice, if I go and I highlight over here, this is alpha D-glucose. So on the Fisher open chain sketch, you can appreciate that this is a D-glucose because you notice here is the second from bottom, carbon and alcohol, and notice how the alcohol is on the right hand side. So therefore it's a D-glucose. Now as far as memorizing it, that's a big hint. So you should memorize there's 6 carbons with the aldehyde up top, the alcohol on bottom, and then the second from the bottom alcohol is always going to be on the right hand side. Now the rest of these, which I'll go ahead and I'll highlight in black, these are ones you're going to have to memorize. So as I labeled earlier, carbon 1, 2, 3, 4. So for carbon 2, 3, and 4, you're going to have to memorize. Again, I always think of it as like a game code. So in this case, it would be right, left, right. Right, left, right. Now, as I mentioned earlier, this position of each of the alcohols is very important. You change the position, it's no longer glucose. The enzymes in the cell cannot recognize it. Consequently, if you change the position of one of these alcohols, when you sketch it out on the quiz or exam, it will not recognize it. And I will not give you points because of it. So, let's go ahead and see if we can learn the tricks on this one as well. Let me cross this one out. So in this case, here's my alpha D glucose. So I went ahead again, highlighted the blue, second from the bottom. Carbon and alcohol. The alcohol in blue is on the right hand side, which you'll always find for D, so that's a big hint right there. Aldehyde in red. I'm going to go ahead and duplicate this one. And I'll show you how I construct it. Again, we're going to go ahead and show you the positions. So in this case, the tail is going to start to rotate around. In the Haworth structure, it's like line angle. The hydrogens are implied. So I'm just going to go ahead and move those out of the way. as it starts to rotate its tail backwards. Oops, get rid of that hydrogen. It's like a transformer. Transform. I'm going to bring this up just a bit more. And as I bring this up a little bit more, this alcohol is going to swing over. Now, just like last time, the alcohol is going to form the ether, and the ether will form a anomeric carbon, resulting in a new alcohol. And the alcohol will be in the down position because it's a alpha D-glucose. So in this case, I'll go ahead and I'll form a brand new bond. Oops. And this one is going to pick up a alcohol, and voila. Now let me go ahead and straighten this out just a bit. And usually what we do is we like to rotate it just a little bit more. Notice if the alcohol was on the right side, then it's automatically going to be in a down position. So on carbon 2, the alcohol is going to be down since it's on the right-hand side. Carbon 3, the alcohol is going to be up. Carbon 4, it was going to be down. So think of it as down, up, down, just as you memorized right, left, right. So here is the final transformation. You'll be expected to sketch the Haworth structure for alpha D glucose. Oops. I could also try to trick you, and I can ask you to draw the beta D-glucose, in which case you'd have to do that as well. And if I ask you to draw the beta D-glucose, then again, on the anomeric carbon, you simply make sure the alcohol is facing up and the hydrogen is facing down. If you go back to the slides, technically you don't need to show the hydrogens. So in mine, you can see them. It's out of habit, but I guess if you wanted to, you can get rid of it. I always like having my hydrogen on the anomeric carbon present. But it's ultimately the alcohol that determines whether it's going to be alpha or beta. Again, alpha down, beta up. This would actually be beta, not alpha. And then if I wanted to, I could swap it around. Now it's going to be alpha. Alright, so let's move on. Galactose. The only difference between glucose and galactose, very subtle, but it is the only difference, is that on, if we number this carbon 1, 2, 3, 4, on carbon 4, the alcohol is going to be on the left-hand side of the Fisher projection. Consequently, on the Haworth structure, it's going to be facing up. So compare that one to glucose. Where it was on the right-hand side on glucose, as well as facing down. The only difference between glucose and galactose is that single position of the alcohol. Change the position of the alcohol, it's now galactose, and it requires a whole new set of enzymes for it to be used. Glucose is the most common sugar. It's table sugar. Galactose is milk sugar, very commonly found in milk. It requires a whole bunch of new enzymes again. So, let's keep going. The big difference between galactose and the big difference between glucose and fructose is basically we've moved down the carbonyl group. So notice everything else is the same. Here you have the carbonyl group, left, right, right. This is where the carbonyl group is, but everything else is the same, left, right, right. However, the second to the bottom alcohol is going to go ahead and form a cyclical hemiketal. And now, instead of a hydrogen on the anomeric carbon, it's going to be an actual methanol that's coming off, so to speak. CH2OH. Notice we have the other OH, the brand new OH formed. If the OH is facing up, then it's beta. If the OH is facing down, it's alpha. So this is an example of a beta D-fructose. So fructose is the hardest one to get down, so make sure to practice that one. Let's go ahead and move on to the remaining slides. We talked about the